Okay, so we are continuing with our discussions on Wiener filters. So this is the last type of Wiener filter that we will discuss. So what is this one? But let me erase this part first. So this is IIR, infinite impulse response, causal Wiener filter. So we are assuming exactly the same setup, which is, now I have X of n process and D of n process. They are jointly White-Sands stationary. And I would like to predict D of n, desired process, from the samples of X of n with a filter. Okay. So this is an LTI filter, as you see, but different from the earlier cases. This is an infinite impulse response filter, which is having taps with number infinity, and it's also causal, meaning that over here you see that I'm always combining to generate D of n, an estimate for D of n. I'm combining all the samples xn minus L, where L is from 0 to infinity. Okay. So previously we have studied the FIR case when this upper summation index is P minus 1, and IIR non-causal case when the lower summation index was minus infinity. So we will repeat the same derivation. So what is the derivation? Expected value of D of n minus D hat of n parentheses square is our cost function, which is MSE. And I would like to minimize this cost function by taking its partial derivative with respect to these unknown weights, okay, kth weight, okay. And if I do this, what do we have? We have what we call this orthogonality. I'm not repeating it again because we have done this many times. This is what we call this orthogonality principle. Okay. So what is E of n? E of n is, it is this error. It's a process again because it's the difference of two processes. Okay. So this E of n, or you may consider this, I'm only focusing on this nth sample. So this is the estimation error for the nth sample. Okay. So this is like a estimation of a single quantity. So this is error times xn minus kden, where error is defined like that for the nth sample. So what should we do? Well, I can take these derivatives for all of these unknowns, meaning that I'll be taking derivatives for, let me write it more specifically, for k is equal to 0, 1, it goes up to infinity, because I have an IIR filter and such that. So what should I do? Now I'm inserting the error definition, this error definition, over here. And what do I get? So dn times xn minus k. So after expectation, that becomes rdx of k. So then d hat of n times xn minus k on the right hand side. Okay. So let me write this. Then I have xn minus k times xn minus L in the argument of the summation. If I take the expected value, I get Rx k minus L. Okay. So this is an equation representing, again, this orthogonality principle. So again, of course, this should be valid for all cases. So previously we had a similar equation in IIR non-causal Wiener filter, non-causal case. So only difference was that this lower summation index was starting from minus infinity, meaning that, so this h of L sequence is doubly infinite. It's going to plus infinity and minus infinity. It can take any values in between for the samples minus infinity and plus infinity. Okay, but right now it's not like that because I'm focused on this causal case. Okay. So previously, when it was this non-causal case, we have taken the Fourier transform of this. And by using the Fourier transform of left-hand side and the right-hand side, I was able to express H E to the j omega IIR non-causal very simply as S dx e to the j omega divided by Sx e to the j omega. So in the last lecture we have covered this, okay? Where the Fourier transform of this one is this, Fourier transform of this one is this, because this is simply nothing but a convolution relation. Now can I do the same thing again? That is the issue. Well, unfortunately I cannot do the same thing. The reason is, again I can take the Fourier transform of this, I can take the Fourier transform of that, but I need to enforce the following thing. H of k, let's say, is equal to 0 when k is negative valued. Okay? So I had to enforce this rule. This is a time domain condition, so it's not clear how can I enforce this rule in the spectrum. Okay? So if I take the Fourier transform of both sides, essentially I cannot enforce this rule. So I cannot apply my earlier trick of taking the Fourier transforms. In the earlier case, well, this wasn't an issue because this relation was valid for all k, so I can take the Fourier transform of the relation by processing all k values. But for this one, because of this one, I cannot do it anymore. So what should I do? I need a new approach. Now, let's look at, so this is the new approach. The special case of Rx of k is equal to delta k, i.e., so indeed it's very special, x of n is white noise. Okay. So if I look at that special case, so what do I have? Let me write this equation one more time. So R dx of k, this is L 0 to infinity, H of L. So this is Rx k minus L. Okay. But in this special case, this is nothing but delta k minus L. Okay. So let me run this summation. So summation L ranges from 0 to infinity, but only when L is equal to k, okay, I have 1 over here, otherwise I have 0. So this is equal to k, h of k, this summation, because all the entries are 0 except one of them, okay? The kth entry is then h of k times 1 of this. So provided that, of course, this k is, now my k is over here, okay? If I select my k like that, for example, select k as 5, so there is L is equal to 5 in this range, so I get this, okay? So it's very nice. Well, I see that, so for the white noise input, the optimal, let's say, causal, let me with small c, IIR Wiener filter is, well, h of, let's say, n, rd, let me write epsilon over here, of n, for n, 0, 1, up to infinity, okay? So what is this? For the white noise input, let's say x of n is, for the white noise input, let me write it like this, epsilon of n. So this is epsilon of n, this is our white noise input. So previously I was calling this x of n in this explanation, but in other words, our epsilon k is delta k. Okay? So instead of x, I'm using epsilon this time, just to show that it is white noise. It is a very special case. So the problem is solved for this case. So what can I do in general then? Any ideas? Well, how about this? Can I implement, previously we have studied this, can I implement a whitening filter for this process X so that after whitening it will be white noise? Then I can apply this result? So that will be our attack methodology. So I will be this time again using this decorrelation or whitening approach. So how can I have that approach? So let me have something like this. So this is X of n. Okay. Then I need this whitening filter. So how can I define this whitening filter? So let me write this power spectral density of X. Okay. But in Z domain. We have studied this again before in an earlier lecture. This is what is called spectral factorization. So some processes, essentially generated by LTI filters for our purposes, can be processes generated by a filter whose transfer function is ratio of two polynomials, essentially. Okay, LTI filter and so on. Then such processes can be spectral factorized. This is called spectral factorization, and we will be having examples on this, but we have studied this one before. But I would like to give some details on this. So Q of Z, so this is what? A minimum phase, let's say filter. Again, we have studied the meaning of this, which is a monic polynomial. This is maybe a little bit new, which is a monic polynomial. So what do I mean by a monic polynomial? Let me give more information. Minimum phase, this is then automatically causal, okay, filter, which is a monic polynomial. So I'm assuming a Q of Z in this form. Q of Z is, for example, 1 plus 3Z inverse plus 5. It goes like this. Okay. So what makes it monic? So this coefficient is 1. So the first coefficient, meaning that highest coefficient with highest power. With highest power. The first means, so highest power over here is zeroth power. So that is the thing. Well, now that explains what's going on a little bit. Why do I say so? So if this is Q of Z, a polynomial like this, Q of 1 over Z, let's forget about the conjugates this, it's 1 plus 3Z plus something like that. Okay. So if I multiply these polynomials, well, I get this spectral factorization. It's a double-sided sequence. Immediately we can see that it's a double-sided sequence, and so on. Okay. So that is it. Now, let me look at my notes. Do I miss anything? Let me call this a generic variable, because it may confuse with the variance of this sigma 0 square. Okay. So can I always do this? Of course, any polynomial, I can pull out this first coefficient and make this, a monic polynomial, and then I can combine those coefficients into this factor. It's always possible to do this. So let's assume that this can be factorized. Power spectral density of X can be factorized in this form. We will be having an example soon. Now, I need a whitening filter. So would you agree that this is a whitening filter for this process? Okay. So if this is X, now I have white noise over here. So this is an invertible filter. So let me have sigma 0 Q of C one more time over here. Then I have X of n over here. Okay. then I implement, let's say, filter. So you may say that, of course, these two operations are cancelling each other. That is the reason that I'm getting this x of n back. So I'm actually trying to design this filter, but I'm having difficulties in finding its coefficients, in optimizing its coefficients. Okay. So what do I do then? So what is our task? Given this is d head of n. This is my estimator. So this is plus, this is minus, there is d of n. So this is E of n, isn't it? So this is our setup. Desired process, n sample, estimator, and so on. So let's remember. So this is the whitening filter, since if I process this power spectral density, if I have this process as the input of this filter, okay, then at the output, what is the power spectral density? It is this factor, process power spectral density times this factor, times, instead of C, I'm writing 1 over Z inverse, so there's a perfect cancellation. So I get 1 over here as the power spectral density of the output process in Z domain. Okay, so this is indeed white noise with unit variance. So it's exactly matching our earlier discussion. Okay, so how about this? Now, let me think about this combination of these two as a single filter. Okay, so if I have white noise input, if I know this D, so what is the optimal filter, meaning that IIR Causal Wiener filter, for the estimation of D from this white noise? Actually, it is this one. Okay, so let me call this filter f of Z then. So I know what f of, well not this one, is it, let me call this filter G of C, because I need f somewhere else. Let me call this filter G of C. So can I design this G of C? Indeed, the optimal design is, this G of C is SD epsilon of C. Okay, but I should be careful. This should be again a causal, because of this constraint, it should be a causal filter. So can I do this? Of course, provided that I can calculate, the cross correlation of this and that. Okay, if I can calculate that cross correlation, I can design this filter in this dotted box. So let me write that. So note that the filter in the dotted box has, let's say, epsilon n as input, which is white noise. Hence, this is G of n, let's say, hence G of n, G of C, and G of n. G of n can be set to RD epsilon of n for n 0 to infinity to get IIR Causal Wiener filter from epsilon n to get IIR from epsilon n input for the estimation of D of n. Okay. Note that the filter in the dotted box has epsilon n, okay, as input, which is white noise. Hence, G of n, this, can be set to RD epsilon of n, this result, to get IIR Causal Wiener filter from this epsilon of n for the estimation of D d of n. Okay. So that makes sense. So let me then calculate this, rd epsilon of n. Let's calculate. Because I don't know anything about rd epsilon n right now. Rd epsilon k. Okay. So rd epsilon k is expected value of d of n epsilon n minus k. Okay. That is it. Well, let me call this filter as f of c. Okay, so I have f times g. So what is f of c? But let me write this first. Then this is equal to epsilon of n is equal to, and this is L is equal to 0 to infinity. Okay. So again, so this is whitening filter. We know that this is causal because it's minimum phase. Okay. And we know that it's causal invertible, hence its inverse is this. Okay, so we are using again our earlier knowledge. So since it is causal, I am starting this summation from 0 to infinity. So this is nothing but an LTI filter, so it's implementing this. Okay. So if I include this information, this convolution information over here, so I have r dx of, so I have epsilon n minus k over here. So over here then n minus k minus L. So I have k plus L. Okay. So d of n is multiplying over here. Then I have d times x, d of n, and this one I'm writing n minus k instead of n. So this becomes this. Okay. Which is nice because I know what r dx of k, because at the beginning of the problem, x and d, they are jointly and stationary. I should be able to calculate this. Okay. But let me process this a little bit further. You know. So instead of, let's say L prime is equal to minus L. So this is then L prime from minus infinity up to 0. F of minus L. So this is r dx k minus L. Okay. So this is L prime. So if we do this, so what do we have? Now I see again this convolution form one more time. So this is sequence number 1, sequence number 2, this is convolved. Okay? So this sequence number, let's say this one, is a causal sequence, so it's a one-sided sequence. So that is the reason that after this operation, it's again a one-sided sequence. It's something like that. So how can I write this? Well, this is simply, the variable is k, f of minus k convolution with r dx of k. Okay. Well, then from here, let me go and write this part. So what is st epsilon of z? Okay. Actually, I'm almost done. Because if I can calculate this thing, the problem is almost solved because I need the zeroth sample of this. I need the first sample of this. I'm almost done, but I want to do this calculation in a simpler way. So let me then do this. This is nothing but the convolution relation. So f of 1 over c, okay? I have something like that. So if we have the complex case, so r d epsilon, we have a, we put with red. If I'm not assuming the complex case, but if we had the complex case, then there would be a conjugate over here. Then this would be conjugated. Then there's a conjugate over f. So by definition, this is our dx of k, dx, okay. Then there's a conjugate over here. Then there's a conjugate over here. Now if you take this conjugate, then there's a conjugate over here and over there, okay. If we have this complex valued case, we have something like that. Okay, so that is one of the things. Then, what else? Then, setting, can I construct this g of c? Well, I can construct this g of c as st epsilon of c, but I should be a little bit more careful. Well, what do I mean by that? Well, please remember that this g of n can be set to this, but only for the positive indexes, right? Or non-negative indexes. And please remember that this is cross-power spectral density. So this is a double-sided sequence. So let me write this. This is like a new notation. So this takes the causal part of the argument. Let me explain. So for example, if we have 3z plus 5 plus 4z inverse, and if you evaluate this causal part operator, so something like this, let's say, okay, then what do we have? We have a 3 over here at minus first leg. We have a 5 over here, and we have a 4 over there, okay? This is n, and this is the sequence in time domain, okay? 0 and first leg, the rest is all 0. So what is the causal part of this sequence? The causal part of this sequence is this part. Okay? So anti-causal part is this part. So this is just discarding this part in the polynomial, you may say. And then I'm getting 5 plus 4z inverse. So it's taking the causal part of the argument. Okay? Well, you know, causal part of the time domain representation, okay, this part is again transformed to z domain, but I think our intention is clear. So if I can do this, SD epsilon, if I can do this, then I'm done. Okay, so we have seen this part also. Then what should I do? So I can construct this. So can I do this one? Yeah, actually, I know this one. So I can construct this overall filter right now from x to d head of n. Then IIR causal filter in z domain is, this is simply this f of c times g of c, right? This times that. And this is equal to, f of c is this, 1 over sigma 0 q of c. So how about this one? Well, the combined block is this, st epsilon of c. Okay, but what this one is this one. So this is, okay, let me write this. Okay, so I have something like that. Let me write this bigger. Okay. Now again, let's introduce the definition of f over here. So I have f 1 over z conjugate is inserted. So there is a sigma 0 over here. And There's a conjugate also over there. Okay, so let me move the sigma 0 because it's just a scalar positive quantity over here. Okay, so s dx f of 1 over z conjugate. Instead of z, I'm writing 1 over z conjugate and taking the conjugate afterwards. That is it. So indeed, this is my IIR causal filter. So that is the end of this derivation. Okay. It was different from the previous one, but we have made a great use of this whitening operation. So after the whitening, from here to this predictor, optimal filter is very simply set as actually this. Okay. So it's easy to combine, find the combined cascade effect of these filters, provided that in an optimal sense, the input is white noise. Okay. Okay, so what should we do? So let me do a comparison. Let's compare this result with this IIR non-causal optimal filter. Okay, so how can I do this? Please remember, it is something like this. IIR non-causal is this. So this is s dx of c over sx of c. Previously we have written it at this corner, okay, at the beginning of this lecture. So if I write the spectral factorization of this, now this is equal to sigma 0 q of c, q of 1 over z conjugate, and we have s dx of c. Okay. So it's almost like that, apart from this, causal part operator. Okay, you see they're almost like that. So we see that, well, this part, let me put a 1 over here, this is nothing but our whitening operation actually. If you check this is the whitening operation. So from this non-causal filter, there's a whitening operation followed by something else. But this, we are taking, this is the non-causal part of this. Non-causal part of the filter. So this part is creating this non-causal response. Okay. So we are taking its causal part, and that becomes the optimal filter. Again, that's also nice. So we are seeing that there is some link or consistency between our earlier results. Okay. Very good. So let me write this minimum error. Well, it's always the same expression for the minimum error in time domain. Let's also calculate or write the expression for the minimum error. Write the expression for minimum MSE for this one. So how do we do this? Well, I need to find E of n, this. So this will be the minimum error for IIR causal. Okay. So how can I write this one? This is expected value of E of n times D of n minus HIIR causal of L x n minus L. Okay, this calculation. So again, this is D minus D hat. So I'm at this point. Now, as we have said before, this is equal to, this is E of n times D of n minus, there's another expectation over here, but this part, but this is equal to 0 by orthogonality. I'm not getting into details. The reason is there is a multiplication of error times xn minus L. Okay, so this is one of our observations. Clearly I'm using these observations to generate the estimate. So because of the orthogonality principle, E times X is equal to 0. So what is E? Error of the optimal estimator times the observation. Okay, the input for the optimal estimator. So they are orthogonal. Because of that, this is equal to 0. Now, again, if we substitute error over here, so I get D times D RD0 minus 0 to infinity IIR causal of L. Then what do I have? I have D multiplying E R D, so D is over here, L. Okay. So this is always the same expression. In other words, so for FIR filter, this upper summation index is limited to P minus 1. Okay. For IIR non-causal, then it's summation from minus infinity to infinity. For the causal one, summation from 0 to infinity. Okay. So only the indexes of this, summation, upper and the lower limit of this summation is changing. Okay. That is it. And of course, this is expected because it's just linear combiner, and I'm changing the length of this vector by allowing it FIR, IIR, etc. Okay. So let's have a numerical example. So this is one of our earlier examples. It's a running example. So let me see. So we have this filtering setup, D of n plus V of n, and we have our D of k as 0.8 to the absolute k as autocorrelation, then our V of k as sigma v square, but this is equal to 1. Okay. So again, we have solved this example previously for the FIR case and IIR non-causal case. So we are redoing it for this case. So what's the question? Find optimal IIR non-causal, let's say estimator for D of n. Okay. So that is our task. So what's the solution? So we are actually ready to attack this problem because I know this filter over here. But before that, what do I need? I need this Sx of z. So this is the power spherical density. So in the last lecture we have derived this. So this is, please remember, z transform of 0.8 to the absolute k. This is z transform of, this is delta k. Okay. Then if I do this calculation, what do I have? So this is derived in the earlier lecture, previous lecture actually. This is 1.6 Okay. So this is what we call this spectral factorization one more time. So let me write this. I want this thing to be equal to a factor QZ, 1 over Z conjugate. And I want this thing to be minimum phase. And a monic polynomial. Okay. So these are our issues. Okay. So how can I do this minimum phase and monic polynomial. This is an infinite polynomial, but it's a monic polynomial. So how can I handle this? So what is minimum phase? You know, poles and zeros should be inside the unit circle. So let me see. So this has a 0 at 2, then this has a 0 at 1 over 2. Clearly, power spectral density. So this has a pole at 0.8. Then this has this factor has a pole at 1.25. This is 4 over 5. This is 5 over 4, then pole locations. Okay. So I have things like that. So how should I select? Well, this should be the Q of Z. Okay. But is it a monic polynomial? Well, let me give it a try. So 1 minus 0.5 Z inverse. 1 minus 0.8 Z inverse. Okay. Let me, do a division. 1. Okay. Plus 0.3 Z inverse. Okay. So if I do this, I get 0.24 with minus. Then if I do the subtraction, I get 0.24 Z inverse. Okay. Plus things like that. Okay. So this goes like this. So it is nice. In other words, we see a 1 over here. It's indeed a monic polynomial. And the coefficients seem to be decreasing. Okay. It's decreasing with the rate of, if you check this, no problem with 0.8 because of this recursion type structure. But for our purposes, now we see that indeed this is a causal sequence because this is one of our process generating filters in this representation. So I see this as a causal sequence, or let's say causal polynomial. This is monic. So no problems. I can always, if I have a term like this, if you do this operation, you can immediately see that this will be a monic polynomial, and look at its poles and zeros, decide whether it is minimum phase or not, and then you are done. So if this is the case, now clearly this is Q of 1 over Z. So since the coefficients 0.5, 0.8, since everything is real valued, these conjugates are not doing anything. Okay, so you can neglect conjugates in this calculation if you wish. Okay, that is it. Then this becomes sigma 0 square also. Okay, so are we ready? Almost ready. If I can find this, then I need to do this kind of an operation. Okay, so where is the eraser? So let me write it over here. Let's get ready for this. Okay, so S dx of C. Then what is S dx of C? Well, this is SD of C. The reason is, well, this is this kind of an operation. Well, if I multiply this x by d sequence, let's say dn minus k, something, okay, dn minus k, then I get rd of k over here, and d and v, they're uncorrelated, 0 means, so I get a 0. So I have this. Essentially, I have something like that. So what is the case then? Now I have to implement this. Then let me also write it over here. So this is Z transform of this, and this was, let me see, again in the last lecture we have written the expression for this. But let me make sure, 64, okay. Okay, I have that. So this is Z transform of autocorrelation sequence Rd of k, which is 0.8 to the power absolute k. Okay. Then what should I do? I should do this division. Then S dx of Z divided by Q. Let me put the conjugates just to be compatible with this. What do I have? 0.36 times. So this is Q, but I need 1 over Q, and actually I need this one, okay, 1 over of this. 1 minus 0.8 Z, 1 minus 0.5 Z. Am I correct? Q is this. I'm putting 1 over Z for Q, okay, and writing its reciprocal because I need 1 over Q. Okay, I have something like that. So we see cancellation of this with this. So this is 0.36, 1 minus 0.8 Z inverse times 1 minus 0.5 Z. Very good. So I need to calculate this causal part right now. Okay. So I have calculated this argument. So I need to find the causal part of this. So clearly, this is a double-sided sequence. Otherwise, if this is not a double-sided, if it's a causal sequence, then it would be, previous result. IIR non-causal, this will be identical to the IIR non-causal result because I didn't need to have this. So there is a need for separating this causal part over here. So how can I find the causal part of this? So it's a double-sided sequence. Okay. So how can I find this causal part? So at this point we need our Z transform, region of convergence knowledge, and so on. Let me look at this pole zero diagram. Okay, to find this causal parts issues. So S dx of C, so this has a pole at, let me mark this unit circle. So this is my unit circle. So there is a pole at 0.8. Okay. And there is another pole at 1.25. Okay. This is due to this. How about the other one? So I have this one, right? Q of 1 over Z. So this has a 0 at 2, but zeros are not very critical, but let me mark zeros also. Okay, so this is this. 0 at 2 due to this term. And this has it has a pole at 1.25. Q of 1. Oh, okay, sorry. I should be more careful with this because I should check it over here. Now I'm looking at this term actually because I need not this one but 1 over Q1 over Z. This is what I need. So I see a pole at, this is pole at Z is equal to 2. Pole at 2. And I see, because of this term, there is a 0 over here. Okay. So these two are pole zeros of Q 1 over Z 1 over. Okay. If you wish, I can put this conjugates like that. Okay. And these two are poles of this one. S D of C. Okay, so what can I say? From my Z transform information, so I know that there's a cancellation over here, but there's again an issue over here. So let me mark these critical parts. Okay. So in the Z transform calculation, you should be careful if you have a product like this. Where is that one? This one multiplied by another term. So both of their Z transforms, they have their individual region of convergences. And for both of them to be valid, you should be working in the intersection of their region of convergences. Okay? So for example, S dx of C. So what's the region of convergence of this one? So poles of this. So this is a double-sided sequence. Now this part is the region of convergence. Okay, so this is region of convergence for S d of C. Okay, from 0.8 to 1.25 radius, there is a ring. Okay, so this is this part. So this is valid when we have such a case. How about Q of the other factor, let me say. The other factor is this factor. 1 over Q, 1 over Z. Okay. How about that one? Well, Q of C is something like this. It's a causal filter. Then Q of 1 over Z is, so this is an anti-causal filter, Q of 1 over Z, because if you write instead of this, if you replace Z's by 1 over Z's, you get an anti-causal filter. Then what do we have? Then what we see is the following. For the other one, the region of convergence for this one is, well, this one, 0 point this and this. So this is the pole location, and what should I say about that one? Well, if we say that the region of convergence of this term is outside of this, circle with radius 2, then that would be a causal sequence, right? So we see that for this sequence to be non-causal, 1 over Q, 1 over Z, it should be, including the inside of this circle with radius 2. Okay. Then their intersection will be again this red part, which is very good because this red part includes this unit circle, meaning that I know that if I design a filter like this by their ratio, I know that it will be a stable filter. Okay. Which is good. That is from our knowledge of Z transform, because this part includes this unit circle over here. Okay, so now this is valid for Z element of, let me call this region A. So this is for Z in region A. Okay, let me call this region A. Okay. Now, then, how should I calculate this? 0.36, 0.36, 1 minus 0.8, Z inverse, 1 minus 0.5, Z. I need to find this causal part. So, I will do partial fraction expansion. So, let me write it like this. What is this? So 0.36. Well, I prefer to have partial fraction expansions with Z inverse variable. So because of that, I don't want to see a Z over here, but I want to see a Z inverse. So I will multiply numerator by Z inverse. Okay? Denominator by Z inverse to get rid of this Z. So I have 0.36 Z inverse, 1 minus 0.8 Z inverse, then I have Z inverse minus 0.5. Is this clear? Because I want to treat, well, we have done similar thing before long time ago in a lecture. I want to treat this thing as Z inverse, let's say Z inverse variable. And I want to do my partial fraction expansion with this Z inverse variable. Okay? The reason is, well, maybe you can remember, Z transform of alpha U of ns, this is the causal part, causal sequence. This is equal to alpha, this is what? Alpha to the power n U of n. So this is equal to 1 over 1 minus alpha Z inverse. Okay? Then we had another relation like this. So Z transform of minus alpha to the power n U minus n minus 1. Okay? Okay. So these parts are the same as you see. Z transforms of this sequence and this sequence, they are the same. But what is different? The region of convergence is different. So this is Z greater than alpha. This is for magnitude of Z less than alpha. This is our basic Z transform information, right? So again, this region of convergence plays a significant role. Okay, so why do I want to mention this at this point? Because I have Z inverse over here. So if I do partial fraction expansion with Z inverses, I have polynomials with Z inverse so that I can make use of this information immediately. Okay, then let me write this 1 minus 0.8 Z inverse plus this is Z inverse minus 0.5. Okay, so when this factor, so how can I do this partial fraction expansion? So instead of Z inverse, if I write 1.25, then this becomes, as you see, 0. Okay? I get a pole. Instead of Z inverse, not Z, I'm writing 1.25. Okay. So how do I do this partial fraction expansion? There is a K, there is an L. I want to find this K and L. Okay. So let's do it this way. So instead of Z inverse, I'm writing 1.25 over here, divided by 1.25 minus 0.5 for this. Okay? If you don't know this calculation, maybe you should practice, if you cannot, not know, but if you cannot remember, let's say, this calculation, please, if I'm doing it correctly, check your notes, okay? So let's see. So for this one, instead of Z inverse, if I write 0.5, okay, then I get 0.36, 0.5 divided by 0. I'm writing 0.5 over here, 0.4. I have something like this. Okay. So how can I simplify this? So this is 0.75. Okay. So this one is, if I divide by, this is 5 over 3, I guess. This part is. Okay, 5 over 3. Then if I further, okay, then this part is as a whole, this is 0.6. How about this part? This is a little bit easier. This is 0.6 divided by this. I have 0.6 times 0. So this is 0.3. Okay? I have something like that. Let me erase this. So if I then continue with this, I get what? 0.6, 1 minus 0.8 Z inverse, this continuation, plus I had a 0.3 Z inverse minus 0.5. But let me check. Is this the right answer? Okay, it is right. Now, in order to use this, well, let me multiply both sides by -2 for this one. Okay. Then I get 0.6, 1 minus 0.8 Z inverse plus, so I get 1 over here, 1 minus 2 Z inverse minus 0.6. Okay, I get something like that. Multiply by -2 plus 1, -2, and so on. Okay, now inverse Z transform calculation. So what was my task actually? I was going to calculate the causal part of this. So I need the causal part of this. I need the causal part of this expression. Okay, this is this. So what is the causal part? And of course we should remember, to understand that causal part, we should look at the region of convergence. Well, in this region of convergence, so there is a pole at 0.8. Okay. Over here there is another pole at 2. So this forms the causal part. The other part forms the anti-causal part in this region of convergence, in region A. Okay. Because why? In region A, this pole location is over here. So it's, on the, so the region of convergence is at the outer side of this inner circle. Okay. So this forms the causal part. This forms, let's say, the anti-causal part. Okay. Actually, I can calculate what that causal part is, what that anti-causal part is, so on, from this information. But I don't need it immediately, but I see the following. So, this thing (0.36) divided by 1 minus 0.8 Z inverse and Z inverse, 1 minus 0.5 C has this causal part of 0.6 Z inverse. Okay, that is the causal part. Okay. So as you see, you need to use your information about Z transforms somewhat carefully for this calculation. Okay. Now, we are almost done. So what is then IIR causal Z? 1 over sigma Z square Q of C, okay, times this thing. So I'm writing this one more time. S dx of C divided by this. Okay. So what was our Q of C? So this was, I remember, this is 1.6. Q of C is 0.5 Z inverse 1 minus 0.8 Z inverse. Is it Q of C? It is correct. So this is this, and this is just, we have calculated this, the whole thing. Okay, is 0.6 and 1 minus 0.8 Z inverse. 1 over 1.6 times reciprocal of this 1 minus 0.8 Z inverse 1 minus 0.5 C times this 0.6 1 minus 0.8 Z inverse. Okay. I have such a case. And again, we see a cancellation over here. And this is, okay, this is 6 over 16 or 3 over 8. Okay, 6 over 16 or 3 over 8. So then this is equal to 3 over 8, 1 minus this. So this is the end of this calculation. So this is H IIR causal Z. Or let me have it like this. Okay. So this is the end of this. So let me write this in time domain. Well, I'll use this. Then HIIR causal N is 3 over 8. Okay. This is 0.5, 1 over 2 to the power k. So N. This is U of N. Well, this thing. Okay. That is it. So let me calculate this error. Then J min IIR causal. Let me use this RD0. Let me write that in case. Yes. 0 RDX of K. Okay, let me write this. IIR causal. Then this is RDX of K. So if I substitute values, this is RD of K, which is 0.8 to the absolute K. Okay. So I get over here 1. K is equal to 0. I get 1 minus. This is 3 over 8. Let me put this, okay, 3 over 8. 1 over 2 to the power. And this is L. Okay. 1 over 2 to the power L. So RDX of, this is 0.8 to the power L. It's absolute L, but L is positive over here. So it doesn't matter. So this is equal to 1 minus 3 over 8, L0 to infinity. 0.8 divided by 0.6 to the power L. Okay. So this is 1 minus 3 over 8. Geometric series. 1 minus 0.4. Okay. So this is 0.6. So 0.6 is 3 over 5. This is 5 over 3. 0.6. 3 over 5. 5 over 3. 3 cancels. So 1 minus 5 over 8. Okay. So this is equal to 3 over 8. Okay. That is it. Well, very good. So that is the end of this calculation. So we have implemented, not implement, we have designed an IIR filter which is causal and estimating D of n with the minimum mean square error. Okay, so let me say a few things. So let's summarize our findings on this example. So let me see. So previously we have derived a one-tab filter, two-tab filter for the same problem. Then we have derived IIR causal filter. Okay. Then IIR non-causal filter. So let me see. So what was this? H of n for this one is 0.5 delta n. For this one is 0.4048 delta n plus 0.2081. So we have done this in earlier lectures actually. IIR causal, we have derived it in today's lecture. So this is 1 over 2 to the power n un. Okay. And this one is 0.3, 1 over 2 to the power absolute n. Okay. So if I have, you know, a table like this, so let me write the errors over here. So this is J-min. So this is the minimum MSE. So this is, let me write MSE achieved by this filter. Okay. So this is 0.5. So this is 0.4048. This is, we have just calculated that 3 over 8 is 0.375. And this is 0.3. Okay. So what do we see? So for the same problem, if I decide to implement, you know, a two-tap filter, then the optimal coefficients are something like that. Okay. And the error is this one. Well, to generate an output sample, you are just linearly combining last two samples that has arrived up to that time, okay, with these weights. Well, for this one, you are combining infinitely many, you know, earlier samples with different weights, as you see, decaying weights, and you get this error. Okay. So you may say that I will never have an infinite length, you know, input. Infinite length inputs to generate a single output. Okay, this is an IIR filter. It has to be, you know, to achieve this performance, it has to combine all of these, you know, sequences from minus infinity up to that time. Okay, so it's a, as you say, an infinite length impulse response. So to reach this MSE performance, then it has to combine all the samples in the history. Okay. So this one is combining all the samples in the history and in the future of that sample, as you see. And I'm assuming that in the history, this process is starting from minus infinity and it's going to up to negative, from minus infinity to the positive infinity. So it's combining doubly infinite number of samples, let's say, to get a single estimate. So we see that the error is, of course, reduced. But as a performance metric, maybe if you implement a, I don't know, 10-tap filter, and if you get very close to this, then you can say that this is probably the best thing I can do, because I cannot combine infinitely many samples and I will never reach this performance level. But if with a 10-tap filter I can reach, you know, performance close to this one, maybe that is good enough. Okay. So these are the main engineering discussions. So these two filters can be interpreted like an upper bounds for the performance, and by increasing the number of the taps, you are reducing this MSE, and you are comparing the performance with the upper bound. On the other hand, maybe you design a 50-tap filter. For the 50-tap filter, to produce a single estimate, you are doing 50 multiplications, isn't it? Because, you know, there's a linear combination with 50 weights. But this one, if we implement an IIR filter, then the computation complexity is much more reduced because of this IIR structure. So if you don't want to implement a very long filter, maybe you prefer to implement something like this. Okay. But in practice, in general, you try to implement very short filters. And using these short filters, you try to do your best. Okay. So you design an FIR filter, which is best performance possible. Well, that is it. So this is our last topic on Wiener filters. So our next lecture is again some parameter estimation, but this is a different type of parameter estimation. It will be basically on non-random parameter estimation, and we will be discussing ergodicity problems and best linear unbiased estimator, which is called blue estimator, in the next lecture. So we will continue from this topic on in the next hour. Okay, thank you very much. See you all later. Thank you.